Hello, everyone. Thank you very much for joining this seminar. Andrew couldn't be here. Rose, I don't know where she is, so I'm just taking over, introducing Kostas Antoniadis, who's giving the seminar today on red supergiants. Kostas did his master's degree in Amsterdam and is now finishing up his PhD in Athens. So I think he will leave today. I don't know if you're still available after the seminar for some talks.
I will leave late afternoon.
So you can find him in my office or in the coffee room. So if you have questions or want to talk with him, you can find him there. Kostas, go ahead.
Thank you. So I'm happy to be here to present this interesting topic on red supergiants. Let me start with an outline of this talk. So I will start with an introduction on red supergiants and their winds. Then I'm going to present my work on the Maslow's rates of red supergiants in the Large Magellanic Cloud, and then investigating their metallicity dependence, studying different galaxies. And after that, I will present you two other works from our group, a bit briefly, about the effect of Maslow's in stellar evolutionary models, and then about a dramatic transition that we found of an extreme red supergiant to a yellow Hilbert giant. So starting with this introduction, what is a red supergiant? They are evolved massive stars with initial masses from around 8 to 25 solar masses. And they have cool temperatures. That's why they are at the upper right part of the HR diagram, and they have large radii compared to the other stars. And here we can see how a red supergiant evolves, starting in the main sequence phase at a hotter temperature, where we have a hydrogen burning core. And then when hydrogen is depleted, the core contracts, the envelope expands, leading to lower temperatures and larger radii, and we have the helium burning starts at the red supergiant phase, and we have a highly convective envelope also. And why Maslow's is significant at this stage? First of all, you can see that it can be around 10 to the minus 8 to 10 to the minus 3 solar masses per year. This is a large dispersion that we're going to discuss. And it can have important implications for stellar evolutionary models, depending how high it is or not. And this, in turn, will affect also the type of the resulting supernova, and maybe it can be a solution to the red supergiant problem, which is the problem of the lack of observations of red supergiant progenitors of supernova above 20 solar masses, although recent studies show that this may not be in the end a problem. It can be a lack of statistics, or even recent studies from the past year showed that estimations of the luminosities of the galactic red supergiants were wrong, leading to wrong estimations of initial masses. So what is the Maslow's mechanism of a red supergiant? It's still quite uncertain. Actually, this figure is from a project from this institute. So we know that red supergiants are pulsating, and these pulsations can lift off some material at outer radii where it can go off the gravitational potential. But then there is a missing force to drive this mechanism, and recent studies that show that turbulent pressure is this force that can lead to the drive of the material outside of the potential. And then at outer radii, when it gets at cooler temperatures, molecules can form dust, and then radiation pressure can enhance also this mechanism. So other implications of the red supergiants and their winds is that we know that all the elements that you can see in this figure now are formed inside in the stellar interior of massive stars, and then after the core collapse supernova, it contributes to the chemical enrichment of the galaxies, and in turn, the wind and the supernova feedback contribute to star formation and the cycle of life of the stars. Here now you can see different types of stellar winds. The plot shows the Masslow's rate versus the luminosity for different types of stars. And the red supergiant phase is pointed with red, some prescriptions that were used commonly in the past. And you can see that the winds are much stronger than the main sequence phase used usually by the prescription by Fink et al. And okay, now before going to the results, I want to mention a bit of this work was part of the ASSESS project, an ERC funded project, which was investigating the episodic mass loss in evolved stars, massive stars. And we had different results from this work. This is our group, from machine learning algorithms to classify the type of massive stars, to spectroscopy of thousands of dusty evolved stars in different nearby galaxies in a range of metallicities, and then using spectral energy distributions, modeling and fitting to derive parameters mainly for red supergiants and their mass loss rates. And in the end, also using stellar evolution models to compare and see the implication. So starting here with the motivation behind this work is this zoo of mass loss relations that exist in literature. Now on the right plot, you can see the mass loss rates versus the luminosity from a work from Yang et al. 2023, which was also from our group. One of the largest red supergiant samples in the SMC, where for the first time also we observed a kink in the relation around 4.6 in luminosity. And also you can see that there are so many relations that they differ by 2 to 3 orders of magnitude. And this is mainly because different studies are from different galaxies, meaning different metallicity environments, which we don't know if it affects or not the mass loss. Then different sample sizes, most of them are small sample sizes around, we can say, tens of red supergiants, and different assumptions, which is the most significant, as I will show you that it can lead to much different results. This now I denote with orange the most commonly used prescription in stellar evolution models, the De Jager et al., but this study was only for around 10 red supergiants and is a study from the 80s, so we need to improve this. And most of these studies are empirical relations based on the dust cell properties, as I'm going to show you how they are derived. So starting now with the mass loss rates in the Large Magellanic Cloud. This was a work that was published a year ago. The sample of red supergiants that we got was photometrically selected from the color magnitude diagrams. As you can see here with red, we know that red supergiants occupy a distinct population. So we got catalogs from the literature, and combining them, we ended up with around 2,000 red supergiant candidates, after also applying some photometric criteria. Then we used the radiative transfer code to model the dust cell that is formed around the red supergiant, assuming steady state winds with a constant outflow velocity. And what dusty does in the end is you have an input of a stellar spectrum, and then it solves the radiative transfer equations in the dust cell, and it gives us as an output the emerging flux. And I'm not going in the details of all the parameters, but then fitting models, we can get the optical depth, which is the most significant. It shows the let's say, the thickness, how dense is the dust cell. And then using a relation, we can estimate the mass loss rate. Another factor that is significant is the gas-to-dust ratio, because we probe the mass loss rate getting the dust cell properties, so how much dust is produced, and then we need to infer how much gas leaves actually the star. So this, we assume an average value from the galaxy. And this is important for the uncertainties in the end. And then we proceeded with SED fitting. We gathered photometry from the UV to the mid-infrared to fit the models, shown with a black line. And you can see that the most significant part to derive the dust cell properties is the infrared, where we'll have the dust emission shown with a dotted line. And yeah, you can see the so-called also silicate bump that it's from the dust around. And then there were also some non-dusty red supergiants. As you can see here, there is no infrared excess, and they're fitted with our lower value of the optical depth of our grid. And these serve, we use them as upper limits in the results. So this is the main result. You can see the mass loss rate versus the luminosity. These upper limits are referred as the gray triangles, and then the color shows the optical depth, so the yellow, let's say, or green are the most dusty ones. And the circles denote the ones that have also spectroscopic classifications of a red supergiant. I should mention also this red star denotes the WHG64, the extreme red supergiant I'm going to talk in the end of this talk. And the interesting part on these results is, again, we observed this kink at around 4.4 in luminosity, as it was observed also in the SMC, showing an enhancement of mass loss after this point. And trying to figure out why it happens, we found out that it relates also with the variability of the star. Now on the right, we have the median absolute deviation of the WISE-1 band. This band is around 10 micron. So, and it probes, let's say, the intrinsic variability of the red supergiant. And you can see that the kink is roughly located at the same position. So the mass loss correlates with variability. Then we proceeded to investigate what is the effect of different assumptions, trying to figure out why all these relations in the literature were so different. And we found out that by assuming radiatively driven winds as the mechanism in red supergiants, which was also assumed in the past that this mechanism is assumed that it contributes to AGB stars, so then people thought that red supergiants have the same mechanism. And you can see with orange points that this, compared to our previous result, this leads to higher mass loss rates by 2 to 3 orders of magnitude. And but this could be unrealistically high, as I'm going to show you also stripping of the star at high luminosities. And also we found out if we use a smaller grain size in the assumptions, the grain size of the dust cell can also lead to different results by a factor of 20, let's say. So now we can compare our study with other prescriptions from the literature. So now with blue dust line, you can see the results from Bizor et al. 2020. Which was also dependent in the initial mass. And you can see that it roughly agrees with our results because also they use similar assumptions. Then we are a bit lower than the de Jager rates, although within the uncertainties. And then also with the Key et al. 2021, which was the first theoretical prescription, assuming that turbulent pressure is the mechanism. And then you can see the other 3 lines by Yang et al. And Van Loon or Goldman that are much higher. And this is because they assume this radiatively driven wind mechanism, as I mentioned. And another one, a theoretical study that came up last year, is by Fuller and Tuna, that showed also an agreement with our results, not so much maybe for low luminosities, but the rest seems in agreement. And then we proceeded to derive a relation as a function of both the luminosity and the effective temperature. You can see on the right the plot with the effective temperature, and we observe an anti-correlation with that one, which is actually have been shown in previous works too, and is expected because at later evolutionary stages we have cooler temperatures. And so also this dependence on the effective temperatures accounts, you can see the magenta points is the prediction for the relation, accounts also for part of the dispersion of the results. Okay, now we had these results on the LMC, and we said, since we need to have uniform assumptions in order to compare different studies and samples, how are we going to investigate if there is a metallicity dependence on the mass loss? And so we need to investigate other galaxies. This work is under revision actually. In A&A we received a positive referee report. And so we studied the SMC again, and the 6D22, a sample of galactic red supergiants, and M31 and M33. So going from low metallicity, SMC metallicity, up to solar metallicity. And so this, again, the sample, we used the one from Young et al., and around 900 red supergiants. And we find a similar behavior, similar mass loss rates, the king at slightly higher position than in the LMC, around 0.2 dex in luminosity. And yeah, again, this was observed that the king is related with the variability. Again, we have the MAD diagram here. And yeah, next we also derive in a similar way mass loss rate relation. We observed this similar anti-correlation with the effective temperature. And then we have the results from 6D22. Now here, again, similar mass loss rates, maybe a kink, let's say around 4.6, but there are not so many points. Also the results are more uncertain, as you can see, and this is because we had to remove the Spitzer 24 micron photometry, because at that distance the resolution wasn't enough and it was a bit unreliable. Apart from the orange points, which have also JWST data and are more robust, let's say. And then these are the results for the galactic red supergiants. Here, the interesting part is that we don't observe any kink, and also in the MAD diagram, you don't see correlation with variability. And but this may be because also in the uncertainties of the galactic red supergiants, there are uncertainties in the distance estimations, meaning we have then uncertainties in the luminosity that we derive, and then also, depending on the position they are located in the galaxy, there are uncertainties in the interstellar extinction that we need to account for. And finally, these are the results for M31 and M33. On top is a previous work by Wang et al., and below it's our results. You see in both cases that we find much higher rates, around 10 to the minus 6. And in the end, we found that these results are not reliable because this is in a even higher distance, and the Spitzer photometry, the resolution is not good enough and may take also flux from the nearby environment. So these results, we discarded these results, and showing that this work from the past is not so reliable. So gathering all the galaxies together, we can compare them, and see if there is any metallicity dependence. So you can see here the results in blue from the LMC and orange the SMC, and most of them seems roughly to be at the same scale, so we can't say much about the metallicity dependence. Apart from the shift that I mentioned that there is in the kink between SMC and LMC. And also we compare our results here with the scene 2024, which was based in gas diagnostics, and so we don't have the uncertainties from the dust cell properties that I mentioned. And since we see that we are in agreement, it gives strongest support in our assumptions that we made. And now on the right plot, I have the Maslow's rate versus, let's say, the metallicity, assuming an average metallicity for each galaxy. And with the black squares showing the results at luminosities above 4.5 in order to remove all the uncertainties regarding the kink, if it's artificial or real or whatever. So in the end, even though the error bars account for the dispersion, you can see they are large, we can't say that we observe a strong correlation with metallicity. However, in removing this gas-to-dust ratio that we assume, this phi factor when we calculate the Maslow's rate, because, as I said, we probe first the dust properties, we see that the dust production rate is related with metallicity. So, for example, the biggest samples between SMC and LMC, LMC has higher metallicity, and you see higher dust production rate. And this is actually expected because at higher metallicities you will create more dust. But in the end, the gas-to-dust ratio is inversely related with metallicity, and when we calculate the Maslow's rates, it brings all the results together. Okay, this is the summary of all the results. I think I mentioned all this. And then in the end, we gathered the largest sample of red supergiants in different galaxies till now. And we found this kink that shows an enhancement of Maslow's, and we need to figure out why it happens. And I mentioned that no strong correlation with metallicity. So now, as future steps, to get more robust results, we can probe low and higher metallicities with JWST data in more distant galaxies. For example, very low metallicities at WLM or Sextans A, and supersolar metallicities at M83, which is currently what I'm doing at ESA. I'm doing the photometry, getting the images from these galaxies. And now these are some preliminary results, let's say, a color magnitude diagram, and a rough estimation of the population of red supergiants there in M83. So probably within the next week I will have also some Maslow's rate results from these. And also another thing is non-dust dependent methods like the theoretical or observational that I showed you before could give stronger support in our results and the assumptions we make. And about the kink, if turbulent pressure, as I mentioned, is the dominant mechanism, maybe if we examine the turbulent speeds of from a range of luminosities versus the luminosity of some red supergiants, and we find a kink in that relation, maybe then it's this, the turbulence is what creates it. Or then is there a dependence on the luminosity over the current mass factor, the Eddington factor, that was suggested by Ving and Sabahit a few years ago, which is similar, let's say, to the hot star mass loss from the transition from optically thin to thick winds. Is this happening also to red supergiants or on the dust cell? And then also we can compare, we can say more if we apply the relations to stellar evolution codes and see the red supergiants fades. Okay, now I'm moving on to the next work from our group that I'm going to present you, led by Manu Zapartas. So applying the effect of the different mass loss prescription in stellar evolution models in SMC metallicity. So what we did here, we got 4 different prescriptions. Let's say 2 at the lower regime by Bizor and de Jager, then the higher regime by Yang et al., and which had also this kink, and then the Key et al., one theoretical prescription. And we applied this in, we implemented this in Poseidon, which is a grid of mesostellar evolution models. And these are the results in the HR diagram and the evolution. So now, here each point shows equal time steps, and I think around 1,000 years. And you can see the different results for each prescription now. For Bizor, you can see that at the red supergiant phase, during the most of the lifetime, it stays at that phase. Then from the Key et al. Results, you can see that it stays for not so much in the red supergiant phase, and it strips off the star, moving it to hotter temperatures. These orange points are the post-red supergiant yellow phase, let's say. And this can be for many reasons, actually. This prescription depends on the current mass, so when it removes some mass, it keeps getting stronger. And also it is very strongly dependent on the turbulent speed. So for different values of the turbulent speed, you can get much different results. And also because Poseidon has high overshooting parameters, maybe, and it leads to high luminosities, maybe it needs some better calibration to estimate this. Then the Yang et al. Results, you can see that for low luminosity it stays in the red supergiant phase, but at higher it strips off the star, moving to hotter temperatures. And the Jager rates, it's, let's say, more similar to Bizor. Now it strips off the star at much higher masses, around 30 solar masses. And we can see all the effect on the results better in the luminosity function, showing the average effect of mass loss, let's say. So here you can see the dotted and dashed gray lines, the luminosity function from observations of red supergiants in the SMC. And you can see the de Jager and Bizor prescriptions at high luminosities maybe over-predict the stellar population, even though we'll have low number statistics there with observations. And then the Yang et al. May agree more. But if we see also the final state of these stars in the HR diagram, so here now the contours and the stars show the expected positions of the core collapse supernova when the star ends its life. And you can see that Bizor and the Jager are located around there, which agrees the points show the observed red supergiant progenitors of core collapse supernova. And you see that these two relations agree. The Yang et al. Strips of the stars and predicts also some yellow supergiant progenitors that have not been, let's say, observed till now. And the Key et al. Has all these uncertainty summation that strips completely the star and moving it to hotter temperatures. And now the final topic of this topic is this dramatic transition, let's say, of an extreme red supergiant, the WHG64, to a yellow hypergiant. This is under revision in Nature Astronomy. Again, we had the positive feedback, maybe some better discussion in the interpretation of the results. So this really dusty known red supergiant. Also, you can see here the first extragalactic, I think, close-up image of such a star. You can see also a ring outside of, this is at high radii actually, this star. And this Onaka et al. Work that came out last year. It was the first that observed the transition of this star from red to yellow, but using only photometry. So we did a more thorough analysis, getting spectra too. So some info about this star. It's, as I mentioned, a known dusty star at very high luminosity that was modeled to have a dusty torus around it. And it's maybe the most dust-enshrouded and one of the few dust-enshrouded stars in the LMC with very high extinction values, AV above 8 magnitudes. And also it has the highest mass loss rate in the LMC. And you can see here the SED of this star, showing a really high infrared excess from the thick torus, even an absorption here at the silicate bump. So we gather archival photometry, and you can see here the light curve during the past years from different surveys and in different bands, IV and R. And you can see, let's say, a regular to semi-regular variability, which is expected in red supergiants, although in this case it's also very high, around 2 magnitudes amplitude. And the dust line show the type of star through spectroscopy. It was an M-type red supergiant. And then after a point around 2015, this light curve completely changed. It flattened, and even the last year, let's say, it shows a decrease, a deepening, which can be an outburst or something. And here are the dust lines are the optical spectra that we have, showing a B bracket T phenomenon at this point. And here is a color diagram with time. So you can see the squares with the V minus I color. So it started as a red star at around 5.5, and then it goes, let's say, to 3.5, becoming yellow. And these are the spectra before and after the transition. So you can see from 2007, the spectrum, it resembles a spectrum of a red supergiant with TIO bands. And then we can see 2 spectra from 2016 and 21 that it shows all these emission lines that show a B bracket T phenomenon. However, if we go to the infrared part, this is an H-band spectrum. Now you can see the spectrum of the star with a background blue line, and overplotted in each case, there are different spectra from known other massive stars, so from a supergiant B bracket T to yellow supergiants here and a red supergiant here. And you can see that it matches more the yellow supergiants. So what we have is, in the optical part, we have a blue B bracket D phenomenon, the infrared part a yellow supergiant. So these are the possible scenarios that we suspect, that it's in a pre-supernova phase with a superwind phase, removing a lot of mass from the envelope of the star, moving it at hotter temperatures, revealing the inner layers. Also, maybe there is a binary component showing this blue component that we see, and the interaction with a binary can also strip part of the star. Or an outstanding eruption like a known galactic red supergiant, VAR-A, that was the only case we saw something like that. That was an eruption of over 30 years, moving, you can see in the HR diagram, the star moving it from red supergiant to a yellow hypergiant. And this is the location of our star, being a red supergiant. And if we take the temperature, a rough estimate from the infrared part of the spectrum, it will be somewhere around there. Although in the optical part, it would be somewhere there in the hot temperatures. Okay, and that was it. Thank you. I come back to my results, which I'm more confident also to answer questions. And I'm not going to repeat it. I'm just going to say that further investigation for the metallicity dependence with JWST data needed. But this will happen. I'm finishing the PhD in September. This will happen if I find a postdoc position. So thank you.
Thank you, Kostas. Questions?
Thank you for the very interesting talk. One thing I didn't fully understand, so you showed the comparison between the two different models where you have like different mass loss rates in the end, but why is it just a shift by 2 orders of magnitude? Why is not the shape changing? So if I would use different models, I would expect to get also a different shape and mass loss rates. Can you?
Yeah, well, the shape is also, I mean, because the SED won't change in the end, and the optical depth will be the same, so the shape of the SED when we model the SED. And the optical depth gives, let's say, is a significant parameter to give the mass loss rate. So going from modeling some stars at low luminosities with low value of optical depth, so not so high infrared excess, and then going to higher infrared excess. So the shape, I don't know if I explain it right, won't change because the different red supergiants will scale up in the same way from because they will have the same infrared excess. Okay.
Yeah. And which models do you prefer? So you show now here mass loss rates 10 to minus 8, and you compare it to the Young sample, if I understand it correctly.
Yeah.
But you also showed the Young sample where it has 10 to minus 6 as like the lower edge. So
yeah, the Young et al. We had assumed in that work radiatively driven winds. But since recent studies show that turbulent pressure, which creates a constant outflow velocity, is more dominant, and not so much radiation pressure in the dust cell, like AGB stars, because also red supergiants have high radii, so the dust cell will be formed at even higher outer parts. Radiation pressure may not be dominant there, so we don't assume this mechanism. Yeah.
thanks.
Other questions?
Hello. Thank you for the talk. I have 2 questions. One of them is when you first determine your sample, you do this in a color-color diagram plot, as I understood it. How certain are you there that you're not catching binaries or other things that you would expect to be there as well that can influence the shape of your color-color plot?
Yeah, good question. There were studies also from current binary stars, let's say, from the UV excess. Also, we examined the UV excess from the SEDs of our samples and removed that. But even with those, they weren't so many. And in red supergiants, it's expected to be around 20%. So it didn't affect the results so much. Then there can be contamination from AGB stars. If you see the shape there are AGB stars. That's why we also apply a cut at around luminosity 4 to get the more luminous stars, which have probably higher masses. And also here the circles show those that have in the literature spectroscopic classifications, and they are red supergiants. Actually, I have some backup slides. We further investigated that because it's a valid point. Here is in the SMC, we use only the spectroscopic red supergiants. Again, we see similar rates and this kink that exists still. And then if we took the galactic red supergiant sample, was from a compilation of spectroscopic studies. And they had also in this study also the total number of K or M type stars, so similar color that would appear in the color magnitude diagram. And we estimated what is the fraction of red supergiants over these lower mass stars. And above luminosity 4, this fraction is around 60–70%. So, yeah.
Okay, that makes sense. Second question, and you mentioned the fitting, but I didn't fully understand what you did. Is this a grid fitting routine where you change 2 or 3 parameters, if I understood correctly, and then? Yeah,
we have a grid with all the parameters optical depth, the effective temperature, the temperature of the dust cell. So we have the grid of these models and we fit to the observations.
Okay, so the error bars you show, are those the error bars from just the fitting, or also taken into account what you showed that if you use different assumptions, which are not in the grid included, as I understand it, are those included as well? Because you showed that sometimes is like 2 orders of magnitude, right?
Yeah, no, the error bars are not from the radiatively driven wind or node assumption, it's only from the fitting, plus the errors from the gas to dust ratio. Yeah.
Is there, because you showed me now that there is like a bigger sample than I got from the original figure of where you have spectra. Is there a way to do a, because this is the mass loss rates you show here are from the red supergiants from which you have spectra, but fitting the SED, right? I'm understanding that correctly? Yeah. Is there a way to get the mass loss rate from those spectra semi-independently from the SED to compare if you're, because you showed me at the end that you compared to the rates from the SEN, but they're like on the upper right edge of your plot, so it's difficult to say that they are really agreeing with your results, right? Like they are outside of your domain a bit, while if you had this whole sample to compare to, that would be amazing.
Yeah, yeah. No, it's not so easy to get the mass loss rate from the spectra. There are some ideas, but yeah. No.
Okay, cool, thanks.
Thanks for the very nice talk. You spoke a bit about the missing red supergiant problem. I was wondering, so you have these higher mass loss rates. Are you solving the problem because the higher mass loss rates mean that the progenitors of the supernovae are no longer red supergiants, they lost the envelope? Or is it that the mass estimate that you get for them is skewed? So you still have more massive red supergiant progenitors, we're just not getting the mass correctly?
Yeah, the high mass loss rates would solve the red supergiant problem in reality.
By making them no longer red supergiants?
Yeah. But in the end, as I mentioned, we don't see so many yellow supergiant progenitors there. And also, there are, recent, all the studies with the theoretical and different works that show that the mass loss rates of red supergiants are not that high to strip off the star. And maybe binary interaction is needed to do that. But also I refer to you to, there were 2 studies by Healy et al. And Bizor et al. Showing that the red supergiant problem in reality was because when they estimated the luminosities of the red supergiant progenitors from the galactic red supergiants in the past was using not very well calibrated distances, leading to lack of, because then they took the luminosity function to estimate the mass, leading to wrong interpreted mass there. So maybe it's not a real problem in the end.
Right. Thank you.
Yeah.
Hi. Thanks, Kostas, for the nice talk. My question is actually about extinction and extinction maps. Like, of course, for the galaxy, we do have different extinction maps, which are very different also from each other. So I wonder, if you have taken a specific map within your analysis, and how that difference would, because the dust distribution is different all throughout the galaxy, right? So how would that affect then the final rates that you would derive?
Yeah, this is mainly for the galactic red supergiants. Yeah, and I checked 2 different maps. I don't remember now exactly who. One was actually included in the Healy 2024 sample that I took. And the results were roughly the same. They didn't differ that much. Yeah.
Thank you.
a physics question. So I didn't understand this statement at some point that you first show there's this variability correlates with mass loss, at least for your LMC sample.
Yeah.
I think with variability you mean surface variability.
Yes.
But then somewhat later you mentioned that if you looked at all your sample or all your galaxies, then there's no such correlation anymore.
For the galactic ones.
Yes.
Yeah.
Oh, this was not in general true.
For the SMC and LMC, we see the correlation. For the galactic, we don't. Yeah.
Okay. Then my question doesn't apply anymore. I have another question then. So in this mass loss prescription you showed various times, so is this always as function of luminosity? And I was sort of wondering, are there any hidden extra dependencies in there, like effective temperature or maybe radius, or maybe more important, the age of the star? So maybe there's some star that just arrived on the red supergiant area has different properties than one that's turning back later or is midway in its evolutionary phase.
Yeah.
So, and I assume not all these stars are the same age at least. So what's the age dependence here then? Or is this an important factor or not in this derivation?
Yeah, a very good question, and the answer is yes. First of all, I showed also that there is a dependency on the effective temperature. Then there should be also a dependence on the mass and the current mass. Now, in an attempt here by Bizor, they studied different galactic clusters. So knowing the age of the stars, they inferred the initial mass. So they produced a relation dependent also on the initial mass. Although again, the sample was small for, let's say, the high masses. So there are more dependencies. The thing is, it's hard to derive all these parameters. So you can't derive the mass in any other way. Or in theoretical works also there are the mass dependence. Yeah.
Thank you.
Thanks, Kostas, for your talk. I would like to come back to slide 15 and also to the point that was made already by Florian. Since then you show there, or you argue for the variability in the right panel. But actually I have to admit that I do not see too much of a difference between the left part and the right part of that same diagram. Maybe you can guide me through it?
Yeah, I mean, in this plot maybe you can see it clearly, but okay, most of the points are here. If it was a density plot, you would see it better, because there are less than 10% of these points, so it goes like this. Yeah, this is, I don't know if this answer, no?
I still don't see it, but I believe your answer there.
Okay.
And then I would, concerning then the binarity and its interaction, you have mentioned that for the last project on VOH G60, 46, yeah? But how, now in general, how does it influence the outcomes of the first study?
What do you mean the outcomes?
I mean that, you know, the binary fraction will be quite high, since we're speaking here about high mass stars. So binary interaction can have an impact on the mass loss rates.
You mean
if
in
you
the
would compare a single star versus a binary star. So how does that binarity that is not accounted for can have an impact on all of these outcomes?
Okay, yeah. So because that was an extreme case, first of all, that could strip off the star. What I observed when I was taking the binary candidates, let's say in the LMC, that had UV excess from this way, it was that they were occupying, let's say, the lower part of the mass loss rate. And this was because this is not a real result. The effect was probably because the companion, because it's a hotter star, it was destroying some part of the dust, so the infrared excess was lower, resulting in a lower mass loss rate. But this mass loss rate, it's not the real value of the mass loss rate of the result of the star. But yeah, it was around 20% of the sample, and also in this study I removed these binary candidates to have a cleaner sample, but yeah, the shape didn't change significantly. Yeah.
But you were arguing now that a companion can destroy the dust, but that's only when it have a very high UV flux, potentially when it's a white dwarf or so.
Yeah.
And then even then, is that very significant given the total amount of dust that is there?
Yeah. So you mean now if they are interacting, or?
Yeah, I was just wondering on your argumentation now. If you say that a companion can destroy the dust, how impactful that is? What fraction of dust can it destroy? First of all, it should be, or should have a high UV flux then, in order to be capable to destroy dust, since that's not too easy to do. And even then, I would expect that to have only a very small fraction of the total dust amount can be destroyed, given the impact of a companion. But maybe I'm wrong. I'm just asking.
Yeah, I guess so. That's why we didn't see also much difference in the results. So because they weren't, let's say, totally, let's say, much lower rates. They were occupying the lower part of the distribution. Now, if they are interacting binaries, I guess then the percentage will be even lower of these stars, so they wouldn't affect the distribution that much.
Okay, good, thanks.
Thank you for the interesting talk. Well, this slide is actually perfect. So when you look at let's say the lower luminosities, I see there appear to be somewhat like lines in your plot. So yeah, especially with the orange ones. And I was wondering, do you have an explanation for why all these points seem to, or a subset of the points seem to lie on a line?
Yeah, this has to do with the grid we use, so how high resolution is the grid, let's say. So at lower optical depths, it's, let's say, one line has a specific value of optical depth, and it occupies there, this line. It's just a matter of resolution of the grid. Yeah.
So would it, like, if you would increase the resolution of your grid, how much would that, for example, change your conclusion about like a shift in the kink in LMC versus SMC?
No, the shift in the kink wouldn't be affected. They can be slightly less up and down at these points, but the general distribution wouldn't change.
Okay, thank you.
Hey, a really nice talk. I wanted to ask you again, or you can stay on this slide. You talked about the kink for massive stars, which from the optically thin to optically thick driving, and yeah, I mean, if we believe that it should be metallicity dependent, because yeah, you drive from your iron opacity bump, and which is metallicity dependent, and so I was wondering, why don't you see? I mean, okay, you see it shifting towards lower luminosity, and from when you go from SMC to LMC. But for the Milky Way, yeah, is it just because of the lack of data or something else? Or yeah.
Yeah, I'm not totally sure. I suspect the lack of data or these uncertainties in the distance estimation that could shift the point depending which is the real luminosity or not. But I'm not sure exactly why we don't see it there. But as the first part, you mentioned in hot stars it's metallicity dependent because the mass loss is depending on the line-driven winds. So in the iron lines, now in red supergiants we don't have this. So I'm not sure if there will be metallicity dependence or not. If it happens in the dust cell, maybe.
Well, you talked about the turbulent pressure term, right? So, and that's from there, right? So,
okay,
I mean, I mean, that would then make sense. Okay, thank you.
Yeah, thanks.
Okay, let's thank Kostas again. And if you have more questions, you can still find him at the Institute for a few hours.
Yes.